Okay, so we found that the last four terms cancelled. So what is this equal to? Well, this is equal to beta alpha beta over x dot x squared. So if we look at the definition of our conformal transformation, this is indeed a conformal transformation. It's a conformal transformation with omega of x equal to 1 over x dot x. So good. So inversion really is a conformal transformation. That's great. But now look, there's something a little bit interesting. So I think, let me clear some space here. We don't need all of these details. You know how to do all of this. So let's clear this out. And let's maybe just keep the scaling factor. That's maybe an interesting thing to keep around. Um, by the way, so you saw that for translations and boosts and rotations, there was no rescaling of the metric. The metric was just multiplied by 1, whereas for the scale transformation, there was a non-trivial scaling. Here too, we see there's a non-trivial scaling, but the difference between this and the difference between the special conformal transformation and the scaling transformation that we considered before is that omega of x really depends on x. So this is now an x-dependent rescaling. Okay, next thing I want to say about I. Take a look at x mu. So we know that x mu is a length. Now look at x tilde mu. That's x mu over x dot x. Well, if x mu is a length, this is length over length times length. So that means that x tilde mu is inverse length. So what this transformation does is it takes a length into an inverse length. And there's no way of doing that continuously. That's why this transformation is discrete. You can't possibly do that continuously. Now, this might make you think. So this changes lengths into minus lengths, but translation, the parameter was A alpha, which was a length, and B alpha has a transformation, which is inverse length. There were D parameters for A alpha and D parameters for B alpha. So what does this suggest? Let's just write the suggestion over here. So A alpha is a length. There are D parameters. Then we've got B alpha, which is an inverse length, and also D parameters. So what it strongly suggests is maybe A alpha and B alpha are related somehow by inversion. Everything seems to fit. So let's see if we can make that precise. And the way that we're going to make it precise, we are going to do the following. Let's do an inversion. After we've done an inversion, we'll do a translation. And after we've done the translation, let's do an inversion again. And let's see what that does. Let's see what that produces. Okay, so first of all, let's take x mu, and when we do an inversion, this will give us x mu over x dot x. So we just did an inversion. Okay, now let's do a translation. And let's call this a translation by A mu. What will this give us? Well, we'll get x mu over x dot x plus A mu. That's how a translation acts. Not difficult at all. And now what we will do, so let's maybe bring it down here. Now we will do another inversion. And we know how inversion acts. So we should take the coordinate, that's x mu over x dot x plus A mu, and then we should divide by the coordinate squared. So x mu over x dot x times by x mu over x dot x is just 1 over x dot x. So that's the first thing that we get. Then there's a cross term. So we'll have plus. The cross term will come as a factor of 2. This will be a dot x over x dot x. And then we will have the term, which is a dot a. So that's how inversion acts. Let's rewrite this a little bit. And the rewriting that I'm going to do, I'm going to multiply numerator and denominator by x dot x. So we'll get x mu plus x dot x times by a mu divided by, the first one will become a 1 plus, we'll have 2a dot x, and then we will have plus a dot a times by x dot x. Is this related in any way to a special conformal transformation? Well, in this final expression, the parameter of the transformation is a mu. So, and that's a finite parameter. So let's take a mu and let's set it equal to b mu, and we'll let this be infinitesimal. Okay? And let's see what happens when we look at this infinitesimal transformation. Well, this will be equal to x mu plus x dot x b mu. Now let's take a look at the denominator. We've got 1 plus 2 b dot x plus. Now, the a dot a will become a b dot b, but we ignore b squared. So this will be 1 plus order b squared. And now, remember the formula. If we've got 1 plus 2 b dot x, well, if we're working to first order in b, this is just 1 minus 2 b dot x. And there would be some order b squared term that we're not going to worry about. So I'm going to be using this formula now, okay, to write this is x mu plus x dot x b mu, and then 1 over that denominator. Now I use the formula in the box. This will be 1 minus 2 b dot x. And in this formula, of course, I'm dropping all of the terms of order b squared. In fact, in this formula, on this side, there would also be terms of order b squared that I've dropped. And now let's just multiply out these brackets. So we get x mu plus x squared b mu minus 2 b dot x times by x mu. But if you look at this formula that we've obtained at the bottom here, this is exactly the infinitesimal form of the special conformal transformation. Okay? So in fact, it turns out that this formula over here gives us, this is the finite transformation for a special conformal transformation. So this is the finite transformation for the special conformal transformation. A mu is an inverse length. You can easily see from this formula that capital A mu should be an inverse length. And how did we get it? We did an inversion, then a translation, and then another inversion. And that gave us the special conformal transformation. That's the right way to think about a special conformal transformation. Okay, 2 more things to say, and then we're just about done.